Welcome to Ones and Zeros. My name's Ben, and this is the first stream of our new Twitch channel, and also got a new channel up on YouTube, so going to be taking a look at sharing some of my programming that I like to get into. Sorry, just making sure the stream's working properly. So we're going to be looking at doing a bit of programming with this guy, which is a STM32F7 Discovery. So it's a development board that you can get hold of, which is really good for getting into doing microcontroller development and C++ programming as well. So really good way to get into it and learn a few things. So what we're going to be doing today is actually starting to build the basis for a whole project that we're going to be doing with these particular boards. We are also going to be looking at some of other different types of development boards and things on this channel as well as FPGA development and a bit of Windows and Linux programming too. So, but basically, as far as this one, because it is basically a microcontroller version of a computer, has a touchscreen, audio, networking, all of that sort of stuff. We're basically going to start from scratch, and over the series of a bunch of streams and videos, we'll be building an entire operating system for it, so that we will actually be able to compile and run apps much like you would with a traditional computer or a phone or something like that. Obviously not quite as powerful, but we're going to see exactly how far we can push it before it breaks, which is something I always enjoy. So, if we jump to... where are we? That's what we want. Alright, cool. So, we're actually going to create a new project from scratch, set up a folder for it. We're going to set up a GitHub repository for it as well, so that we can automatically push it through to GitHub. And the code from this particular stream and possibly the next stream will be freely available on GitHub. However, if you want access to all of the more in-depth code that we get into over time as well, you can jump onto Patreon, and our highest tier on Patreon will actually give you full access to our entire code library for STM32 series, as well as for the ESP32 programming and FPGA development that we're going to have a look at as well. So that way you can get to have a bit of a play with it. So first up, we might just chuck a folder on our desktop for the moment. Let's give that one a name. Now, the particular project for all of the development we're going to be doing with these videos is called Quartz Arc. The reason why that random name was picked is because the pieces of silicon that silicon chips are made out of is actually grown from silicon crystals and is actually molten quartz prior to them actually creating the crystal that gets sliced up into wafers and turned into chips. And then arc, of course, because arcs are electrical, so it's kind of a natural thing for that. So we're going to jump into GitHub first up, get that fired up, and we're going to create us a new repository for this one. Might help if I could actually type properly. And because there's going to be a few of these, we're going to give that name so that we know that that's for the F7 Discovery board. Still can't type properly. Alright, cool. I'm going to point that to the folder that we've just created on the desktop. And we're going to pop in here and I'm going to create another folder just for this one. So, STM32F7D for that one. Awesome. And create that repository. Alright, So that is good to go. We're just going to tell it we want to publish that one. And although I've selected to keep the code private for the moment, we will, like I said, be making the code from this stream public. At the end of the stream, I'll probably do a clone of this repository and make that one public. So good to go. Let's jump into... So for the development with this one, we are going to use the STM32 CubeIDE, mostly because for beginners getting into this sort of stuff, it can be much easier to use, even though it's not the best IDE, but it is designed to work hand in hand with the STM32 line of devices. So, and especially as far as the debugging tools and things like that, it's actually really good for that sort of thing. It does have a few quirks, but once you kind of get used to that, I think that goes for the STM32 chips in general. Do have a few quirks, but they can be quite good to work with. So just creating an empty workspace, wait for that one to finish loading. Alright, let's create us a new project. Now, we are going to do it using the wizard once it actually loads. What we are going to be looking at doing though is throwing away a lot of the code that the wizard generates for us anyway. But there's just the kind of easiest way I find to get started, because that way it sets up a few things for us, gives us a bit of a folder structure and everything ready to go. Okay, is it actually doing it? Maybe? No? Let's try that again. There we go, it's actually doing it this time. Wouldn't it be funny if it decided to crash on the first stream? That'd be kind of brilliant. There we go. Alright, so we're going to jump into our board selector. We know we're working with a Discovery kit, and we know that we're dealing with the STM32F7. Jump into there. Now it can be a bit confusing with this one, because there's actually two boards, or two revisions of the same board that they released. We're going to select the one that shows that its marketing status is active, and that generally tends to work fine, so I'll click next on that one. Now we could go with either C or C++ with these guys. I've done probably most of my programming with the STM32 line using C code. However, there is some cool things that I've been doing with them recently using C++. My coding style with C++ generally tends to be a bit of a blend of C and C++. I like to use a bit of both of those things, so that just seems to work well for me, the way I like to code. So select C++, we're going to call this STM32F7D, and check if there's anything else we want to change there. That all looks good. Now, if you haven't created a project for an F7 board so far, then what will happen for you next is you're going to get the IDE downloading the firmware library for the device. I think when I did it the other day, it's about 1.2 gigabytes, so just be aware of that. It can take a little while, and that'll happen pretty much as soon as you click finish. However, because we have been doing some coding for this guy, it's already downloaded and we are good to go. I did select not to initialize peripherals in their default states, partly because we're going to be doing all of that anyway, so it's kind of unnecessary. And we'll just give it a moment to get everything configured and ready to go. We'll jump through the Cube Wizard and get everything set up there, and then we'll get stuck into starting to get our file structure and everything like that set up. We're going to, like I said, be throwing away quite a few of the files that this wizard creates. Part of the reason why I wanted to show doing it this way as well is just so that you can see the difference in between the way the wizard generates the code and how the code looks when we're actually doing it from scratch. Although some people mightn't like my particular code style, I do generally try to keep everything really neat. I do like to make sure that as I'm going through a file, especially if there's several thousand lines of code in a particular file, then I want to be able to spot things really quickly. I don't want to have to be trying to dig for particular bits of code that I need to modify or reference or things like that. Alright, so we have our configuration tool set up, so we can see pinout of the particular device that we're working with. And it's only set up a few devices for us, so a little bit of GPIO, the nested vectored interrupt controller, and the system management controller. Now, the clock configuration, I do find this page handy, not so much for setting the clocks up for me, because it's something I much prefer to do myself, but I do find it handy for trying to figure out settings and things like that. So like, for example, in this case, we know we're not running the board off battery or anything like that, so we want all of the performance we can get from it, may as well, just because we can. And it's not going to consume that much more power for that tiny thing by turning it up all the way. So we're going to pop in 216 megahertz for our H clock, and then if we just hit enter, it's actually going to go through and figure out all of the clocks for us. Now the reason why I find this handy is because it can be a good way to sort of get your head around how to set up, or what settings to use for the different PLLs and the dividers for the various buses and things like that. Also gives you a bit of an idea of sort of how the clocks are actually laid out for the device, because as we can see, there's quite a few of them. Even as far as, you know, getting an understanding for how the low-speed clocks, the low-speed internal and low-speed external clocks work for the real-time clock, and for the one of the watchdog timers. So in this case, what we will be doing is using the high-speed external clock, which is a 25 megahertz crystal on the board, and running that through the PLL, this one here, to give us the particular speeds and everything that we need from that. And then onto, we'll be manually setting all of the bus speed dividers and everything like that. But like I said, just wanted to show this particular bit of it, because it can be really useful for coming in and going, okay, I need this particular speed for this peripheral in the chip. How do I achieve it? What can I do to make that happen? And then taking that information and using that to actually manually set the settings in code. This is taking a while. We might see if it'll let us just skip that step like that, because we don't really need to be waiting for that. Right, that all looks good, and there's nothing in tools that we really need. Now, what you'll notice, as soon as you save it, it's going to ask if you want it to generate code. We'll hit yes. Yes, we'll open the C++ perspective, which is what we need to start writing C++ code. Awesome. Let's tidy this up a little bit. Alright, and we'll hide that one for the moment. So, we can see, we'll close that and save it. No. Awesome. So it's popped us into our main.c file, which is funny because we asked it to create a C++ project. That's one of the things that I do find weird with the code generation, is that if we jump in here, all of the source files it's created are C files. Some of them we're going to leave as C files, but we're going to be replacing especially our main and our interrupt handlers file with C++ files, because that's the language that we want to use. You can see that it has gone through and generated a bunch of code for us. It's not completely terrible code. It's not the neatest code in the world either. And you will notice that there's these comments all over the place. The reason for this is because of the automatic code generation. It's intended that if you put your code in the right places in the files, then when you go to regenerate code, change clocks, turn peripherals on or off using the wizard, then it can actually better generate the code. But because we're not going to be doing any of that, we'll get rid of a bunch of it and go from there. Now, I'm personally not a fan of having separate ink and source files. I get that some people are. I like to be able to see what files belong to a particular system in one go. So in this case, all of our core files are just going to be in the core folder. We will keep this startup folder, but first thing we're going to do is chuck all of these guys in here. Now, this can cause some issues for us if we don't go through and set up all our project preferences as far as where our include and source folders and stuff are at a later date, but we're going to go through and sort that out anyway. Now, looking at the various files that we've got here, so we've got our main C and main H, going to be replacing those. We had this HAL configuration file, which basically allows us to go through and define what modules are enabled, so as far as which code is going to basically get included or set up as part of the HAL or hardware abstraction layer. Now, I have seen a lot of comments in the community for STM32 that a lot of people don't like the HAL. Now, I do kind of agree. It's not the most efficient thing in the world. However, for a beginner, it can be really useful using that code from ST Microelectronics simply for getting things set up a little bit quicker. So things like getting drivers written and things like that, we're going to be using the HAL for a decent bit of that. But we will also go through and have a look later down the road at getting direct register access happening for our drivers, so basically overriding the HAL. Now, I use the HAL primarily to help set up the peripherals on the chip, things like that. I don't necessarily use all of its features, so in certain situations, especially when I'm dealing with like serial and UART peripherals, I do a bit of direct register access there. I don't use the interrupt handler setup and everything the way it's done in the HAL. I actually do all of that manually, simply because for that sort of stuff I do want really good performance straight out of the box. Now, while we're in this file, let's go through and we're going to start enabling some of the modules that we know that we're going to use in this project. There may be additional ones, but there is a bunch I know off the top of my head that we're definitely going to be using. So firstly, the analog to digital converter. We are going to be using the DMA2D. It's actually a really cool peripheral. I'm a bit of a fan of that one. I'm going to need the SD-RAM module so that we can set up the 16 megabyte SD-RAM chip that comes on the development board. Don't know if we're going to use I2S just yet. We're definitely going to want the LTDC to run the LCD. Real-time clock and random number generator. And we'll be using the quad SPI to access the 64 megabyte flash chip that is on the board. Alright, so that's those guys. We will be using the SD card, and we will also be doing an implementation of the FATFS middleware as well, which will allow us to access SD cards that are formatted with the FAT or FAT32 file system to be able to open files, save files, all that sort of stuff, which makes it so that we can actually transfer data really easily between a computer rather than having to send everything over serial. We will also be looking at using the FATFS on the flash chip as well, so that we can basically treat the flash chip as if it's a hard drive for the device. We're probably going to be using SPI. We are definitely going to be using timers, and definitely going to be using UARTs. What else have we got? We're going to be using the DSI because that's the thing that sits in between the LTDC and the LCD driver. So it basically streams out the video data so that the LCD module can actually display it. External interrupts, most likely. What else have we got there? Just make sure I haven't actually missed any. That looks good. Alright, so let's save that one. So that file we're going to keep. This file, actually we're going to get rid of the mains now as well. They can just go. Don't want to make our own. MSP file, this is partly for setting up sort of the upper layer of the HAL. We're going to be not needing that anyway, because I don't think I've ever used any of the MSP functions at all. We're going to get rid of our interrupt handler files, because we're going to create fresh ones of those. We are going to keep syscall, sysmem, and this system file here as well. And we're going to leave those guys as just normal C files as well. I'll leave the MSP file here for the moment because we're going to come back and copy out these guys as part of our initialization stuff that we do. What is next? Alright, so let's get some files created in here. Now, don't want templates, I like to just make my files from scratch, so we're going to call this main.hpp. And we want a main.cpp. Forgot to tell it not to use the template on that one. We're going to create a handlers.hpp and a handlers.cpp. These will be where we put our exception and interrupt handler functions. Might pop an S on the end of that one as well. There we go, like that. Alright. Now, we're also going to create a boot.hpp and boot.cpp file. What we're going to be using these for is the initial boot code. The stuff that is required in order to get the device to a point where we can actually start to really usefully do stuff with it. So things like setting up clocks, turning on our caches, setting up the systic timer, all of that sort of stuff will be going in our boot.hpp and boot.cpp files. So we'll pop those in there. And I keep forgetting to tell it not to use awesome, cool. Now, first thing I like to do is basically set up a bit of a header for the file, which we're going to copy and paste for all of the files. Basically, just a bit of a description of what the project is, what particular role each file has, what the file name is, what date it was initially created, who created it, all of that sort of stuff, just so that we can help keep track of it. Although GitHub will be tracking a bunch of stuff for it as well. So we are calling this one Quartz Arc. That's our project name. And let's just copy and paste this guy, chuck this in here, and STM32 F769I Discovery, so that we know what device this particular set of code is for. We will also pop in the date, which today is 22nd of the 9th. Actually, we might do it a bit more formally. I just like the way it looks a little bit better. Again, you're better off getting this stuff right at the start, because having to go through and actually change it in every file at a later date just because you don't like the way it's formatted kind of sucks. Okay, we want the file name, so in this case is boot.cpp, pop that in there. What system is it part of? So in this instance it's part of the core system, so other ones that we're going to have will be drivers. We're going to look at implementing some really cool dynamic interrupt management and things like dynamically managing peripherals like the UART peripherals, things like that. So we'll have separate systems for each of those, so this way we know which system it's part of and what role it plays in that particular system. So in this case it's part of the core system. These guys particularly hold the boot code. Alright, just copy and paste these guys down here. Now, it might seem like something that's fairly simple and unnecessary, but I tell you what, the amount of times that a decently written header has kind of saved me. Sometimes even putting a description, like a longer description of the file and things like that can be good. I don't generally tend to do that. I don't tend to stick to the particular approach of putting massive descriptions with each function and things like that either. I tend to take the approach that well-written code that sits well on the screen, is fairly self-explanatory, it's self-describing, and if you're able to look at the code and tell at a glance what it does, you really don't need a separate description for it. At least that's my take. People that want to do it differently, that's perfectly okay. I have absolutely no issues with that. Now we are going to need... where are we? I'll come back to that in a moment. I don't want split view, thanks. There we go. Alright. So we're going to grab this. We're going to start with our main.hpp file. Now, we are also going to just pop in two more files into here as well, which will be a setup.hpp. Actually, we'll just go with the setup.hpp on its own for the moment. We don't necessarily need a CPP file for that as well. So what this file will be containing is basically a link to the two main HAL files, or two main STM32 files that we need, that gives us access to the HAL and all of the chip features, things like that. We're also going to be popping in here things to define for certain peripherals what GPIO they're using, what pin number they're using, if they're something for a peripheral, so say for a UART or whatever, what their alternate function is that we need to select in order to get that to work properly. Other things I like to pop in here are things like the interrupt request priorities and DMA priorities, so that you can come in and see at a glance what all of the priorities are for the different interrupts, and that way if you need to shuffle the order of some of the interrupts, things like that, we can do that as well. So we're going to pop our header in here, and just going to change this to setup.hpp, and we're just going to call that setup for the moment. Now basically all of our other HPP files are going to include this setup file. This setup file is going to be the one that actually links to the HAL stuff. Now let's have a look at... It's a little bit different doing this live, I must say. I'm not going to find what we need in this file, I don't think. No. However, I believe off the top of my head, and we'll find out when we go to build this, that we should be looking at STM32F7XX.H and STM32F7XX_HAL.H. I believe they're the two files that we need. Now, I did just put a comment there saying includes, and that's some of the sort of thing that I do in my code. There can be blatantly obvious comments that I put in there, and it's not so much to tell me that they're includes, because that's pretty obvious. It's because white space and comments well laid out, I feel, can again help as far as scrolling through code really quick and finding the particular section. It lets your eye settle on it much easier. Or at least, again, it's a personal preference thing, and there's plenty of coding styles out there, and I've got nothing against the way anyone chooses to code, as long as it works and preferably looks neat. You don't want code that's going to be crap for someone when they come along and try and work with it. So, back to our main.hpp file, we're going to include that setup file in there, so that can access all of that. And again, we are going to just pop a includes thing there. That's basically all we're going to pop in this file for the moment. I'm going to jump in here. Now, for our main.cpp file, we're going to include main.hpp, which is automatically going to include setup for us. That's all good there. I don't believe we changed it for this. No, we didn't. Okay, so the role of the main files is they're the application entry point. So we pop that one in there. Hopefully this is not too boring. I do think that although the initial setup and stuff like that can be a little bit boring, it's probably the most important thing. It's like building a house. If you don't have a solid foundation to build everything else on top of, there's no point in having a house. It's just going to come down in the next gust of wind. The other thing we're going to quickly pop into this file is going to be our main function, which will be the first thing that gets called. Not technically the first thing that gets called, the first C++ thing that gets called. We'll have a bit more of a look at that shortly as well. So, now, again, just a personal preference thing. Most of my functions, I'm going to put 2 lines of comment prior to the function. I'm going to put what its name is, exactly what its name is, and what it kind of does. If it belongs to a class, what, is it an initialization method? Is it something that's dealing with data? Is it something that is, say, a control method for a driver class or something like that? Part of the reason why I do that is because I find it easy when I'm scrolling through to be able to see those things jumping out, especially if you've got a really long name for a return type for a function or a method. Sometimes actually spotting its name, the name of the function or method as you're scrolling through, can be a little bit difficult, whereas if you do it this way, the name's always going to be 2 characters off the edge of the file. So int main void, and that is that bit for the moment. We are going to tell it to return something, even though it's never going to, simply because it does have a return type. Basically, we're going to go through setting everything up, and then we're going to go into an infinite loop where all of the processing happens. Similar to what you would do with an Arduino, things like that as well. Alright, so that is that one sorted. I'm going to jump into a handlers file again, put our little header thing in there. And for this one, it will be exception and interrupt handlers. And this one is the HPP file. Alright, and for this one we're going to be including our setup file. Now, let's quickly pop that one into this one as well. And this will be CPP, and for this one we are going to be including our handlers.hpp file. Do our boot as well. Okay, definitely can't type today. That's better. Okay, so this is system initialization, I think I called it in. Oh no, boot code. Okay, cool. Alright, let's just fix that up again. Okay, now this will be including boot.hpp, so we'll do that while we're in here. This one will be including setup. That's correct, we wanted to fix this, right? Okay, awesome. We are starting to get somewhere as far as laying things out. So we're going to quickly set up our exception and interrupt handler functions first up. Partly so that they're ready to go, and partly because there's certain exception handlers that we kind of need, certain ones that we're also going to be using to help us debug things. So if you don't know what an exception or an interrupt handler is, it basically, the way the chip will work is it's going to go through and start executing our code from the entry point. It's going to keep going through that as long as it needs to. However, there is certain things that can trigger the processor to jump out from where it's up to, start executing another bit of code, run through that quickly, and then jump back to where it was. That allows us to deal with certain system errors. It allows us to do things like handling the system tick timer, which is one of the things that we can use to help create specifically timed delays or monitor performance, things like that. So it's basically just a place that the processor can jump to based on a hardware trigger. Now, easiest place to find these, especially because we have already thrown away the original IT files, is if we go into startup here, we're going to see this file, which is actually the very first bit of code that executes when the chip starts up from this code. So it will actually jump in here go through this, which is actually assembly language, and it's going to get the chip basically set up a little bit initially. It's going to run through and call system init and initializing libc and all of that sort of stuff, and then we can see here it's got the bl main command, which tells it to branch off to main, which we just created. So it will then jump from there and continue to execute our code from there. If we keep scrolling, we're going to actually see the list of all of the exception and interrupt handlers, as well as the reset handler. So the reset handler is the very first thing that gets called whenever the chip's reset, and that actually goes back to the very start here. We can see it's the reset handler. It's the very first thing that it executes. We've also got all of these guys, which are exception handlers. And then we've got our full list of all of the interrupt handlers, which there's a lot of. So we're not actually going to set up any of the interrupt handlers just yet, but we are going to get the exception handlers set up, because that's kind of important in order for us to be able to start developing code. So just copy and paste those out to our handlers.hpp file. We're going to do a bit of a replacement on this, so 2 spaces .word, and we're going to tell it to replace that with void, which gives us that, and then we are going to replace underscore handler with underscore handler void, like that. It's going to give us the sort of the start of our layout of our functions. These ones with the zeros, we can just delete them. Don't really matter quite so much. So let's just get all of these sort of laid out a little bit. Actually, that's not what we want. We actually want semicolons at the end of all of these ones, because we're in the HPP file. So we're just declaring them at the moment. We'll actually be popping the definitions into the handlers.cpp file. So let's just pop a bit of a comment in there. Again, just to help break everything up. We're also going to be popping in now, I'm guessing anyone that's watching this that has done C or C++ programming previously may actually be screaming at the screen right now, because there is a certain thing that I have kind of overlooked for the moment, and that is preventing things from being recursively included. Now, that might seem like a bit of a mouthful to anyone that's kind of new to this stuff initially, but it's kind of important. The easiest way to explain it for the moment, until I go more into depth on how includes and stuff work, and that can be a whole thing in itself. It's important to make sure that include files aren't included more than once in a single C++ file when it's being compiled, because you will get compiler errors and they can be a bit weird to find if you're not aware of what it's actually talking about. So the way I generally do this in here is we're going to go if not defined. No, this is the main.hpp file. Make sure my brain's actually working, and we're going to define main.hpp. Now, the reason why we're doing it this way rather than using pragma once, which some people may have seen previously, is that this IDE doesn't know how to handle it, I guess is the right way to say it. I'll show you what I mean in a second. If we jump in here and we try to do this, like we could say do in Visual Studio, it doesn't actually know what the once keyword means. It doesn't know how to handle it, so the easiest way I find to deal with it is just making sure that we have our prevent recursive inclusion at the start and at the end of all of our header files. Also pop a little thing down here so that if we're at the end of the file in a long file, we can see what file we're actually dealing with. So it's important in your header files that basically all of your code goes in between this prevent recursive inclusion statement here and this one down here, in order to make sure that that particular trick is actually doing its job properly, because otherwise it's not going to. So we are going to copy that, jump into our handlers file, chuck that in here as well, and now if any of this seems a little bit glossed over or you're confused or anything like that, feel free to ask questions. That is definitely something I'm open to, trying to help people understand things a little bit more clearly, and some things that seem... that was clever. Some things that might seem simple to me might not be so simple to other people, and some of the programming tutorials I've watched just because I'm interested in seeing how people do things can gloss over things a little bit much. It's kind of like when you see those people trying to show you how to draw or do art or something, and they go from a stick figure to a perfect, like, almost copy of a photo in a couple of steps, and you have no idea how they've done it. Doesn't help you learn anything. So we're going to do the same thing here, but with the bit that goes at the end of all of these files. So handlers.hpp, that, we're going to pop that at the end of this file. This one will be boot.hpp, and do setup.hpp for that one. Alright, back to our handlers. So again, in the process of getting our exception and interrupt handler sort of section of our code sorted out, just going to copy and paste this guy in here, and I'm going to go through and create what will be our definitions for these particular functions. Just going to pop some blank space at the bottom of the file just so that we can scroll through it a little bit easier. Alright. Alright, so that's that one. Now we're going to just copy and paste that particular line for all of these. And we'll pop some names in here as well. So NMI is non-maskable interrupts, hard fault handler, mem-manage handler, bus fault handler, and usage fault handlers are triggered when certain errors occur, such as if we try to access the wrong memory location, or say if we have a pointer to a class that is currently null and we try to access it as if it's pointing to a class. It should, off the top of my head, I think be the hard fault handler that will be called in that case. Now we are going to come back in here at some point and allow some of those fault handlers to actually trigger the LEDs, the user LEDs on the board, so that if it does lock up, we can actually see that at a glance as well. I'm a big fan of using multiple different debugging tools, whether it's using LEDs, printing stuff to this serial or UART so that we can actually get a log of it on the computer, everything through to using the actual debugger that comes in this IDE. I'm a bit of a fan of that. And then if we're doing something like communicating with another peripheral, then I'm also a bit of a fan of getting out the oscilloscope, multimeter, logic probe, things like that to actually see what is actually happening. If you're having trouble debugging a particularly difficult issue, the more tools you've got and the more information you've got to be able to debug that, it's definitely a good thing, even if you don't necessarily use all of that information. So we're just going to go in and we're going to pop in some basically infinite loops in these guys for the moment, because generally if we've gotten to a point where we've triggered one of these fault handlers, we've probably done something where we don't necessarily want the processor to continue running. Or when we come back and look at doing dynamic exception and interrupt management a little bit later down the road, should be coming up in a stream maybe in the next week or two. We'll be looking at that part of it, depends how quickly we get through stuff. We'll actually see how we can build a system robust enough to be able to deal with those issues and just keep going on. Now, we're also going to just pop in here Hal Inktick, because we're going to need to call that one as well. So I've got those all set up for the moment. Now the other thing, which I kind of overlooked back in our HPP file, is when the linker goes through to link everything up. So when you go to build the code, you've got your compiler and your linker. The linker needs to know how to link these particular handlers with what we've just created in the handlers file. So by default, all of these, if we scroll down, we can basically see that if it can't find something that is actually called NMI handler, then it's actually going to fall back to the default handler, which if we scroll back up here in the same file, we can see we have the default handler, and it basically just goes into an infinite loop and keeps executing that same branch instruction over and over again. So it doesn't matter if you don't define, say in this case we're not defining any of the interrupt handlers in our handlers file at the moment, that's perfectly okay. Those ones will go into infinite loops if they're triggered, but by default none of those interrupts are turned on, whereas our exception handlers are. So that's why we're making sure that we deal with those ones first. Now what the linker is actually looking for when it goes to connect these guys up with what we've created here is it's actually looking for C functions, not C++ functions. So if we try to use them at this point and it goes to try and trigger one of them, it's not going to execute the code that we've put in any of the handlers. It's going to go into the infinite loop from that assembly file. So what we can do is leave, might help if we put the right bracket in there. So we're just going to wrap those guys in an extern C statement so that it basically treats those guys as if they're C functions rather than C++ functions. So we've got a little bit of the bare bones sort of set up at the moment. We are also just going to jump into our project properties, make sure that everything in here is set up the way we want it as well. make this guy a bit bigger so we can see what's going on. I need to edit this one because we don't have the ink folder anymore, it's just core. Now, I'm going to edit that for release as well. The smartest thing to do would have been to just select both configurations, debug and release, and then edit it, and rather than having to do it twice. However, we're also going to have to do it for this one as well. So again, we just want core, we don't want core ink. Nice, that all looks good. And our source locations, which it won't actually allow you to view. This is something I do find a bit silly with this IDE, is that it won't allow us to view our source locations if we're going with all configurations, which is silly. We are going to apply and close the settings we just made, and then if we jump back in here, we will actually be able to go in and adjust our source locations now, which both look fine anyway, for both debug and release configurations. Awesome. Alright, now we know in our main we're basically going to be going through and doing system setup, and we're also going to be doing our processing loop, which will basically just consist of an infinite loop, which will be, if you're familiar with Arduino and you're not sure kind of what's going on here, essentially what we're doing is setting up what is like the, I believe it's setup and loop in the Arduino IDE. So all of the stuff in here is essentially going to be our setup code. All of this stuff is going to be our loop code. This is more traditionally kind of how I would do it in C++, as opposed to having two separate functions like you do in Arduino. I'm not going to need to pop anything in there for the moment. However, we're going to jump into our boot.hpp file, and I'm going to create some system initialization functions, as they're not members of class. Alright, so we're going to want to be able to return a value to let main know whether or not the initial system setup was correct, and we could just send back like an integer value or a uint8 or something like that. I'm more of a fan of using an enum for something like that. The main reason for it is because if, in this case, we basically want to know if it succeeded or if it failed, which means we've only got two values. If we were to use an uint8, there's a chance that if someone messed up the code, that you could have any one of 256 different values popped in there, and it's not necessarily going to know what to do with it in certain situations. So the safest approach is to use an enum. We're going to call this QA_result, quartz arc being the reason for the QA, and this is something that we're going to use globally throughout our project. We want that to be a uint8, and we're just going to go QA OK, which will be equal to 0, 0, and QA fail. Now the reason why we make OK 0 instead of fail 0 is because if we want to come in later and add different types of errors rather than just a single fail error, we're going to need to be able to put multiple of them in there, whereas if we made fail 0 and OK 1, it doesn't make sense logically when we go to start adding more. So the next error would be 2 or whatever. If OK is 0 and all of the failures are anything that's not 0, it means that OK is essentially a Boolean false, while any error is essentially a Boolean true. and that makes it easier for us to deal with when we're checking for that sort of thing later on. Let's just leave that for the moment. That will do what we need it to do. Jump back to our boot.hpp file, and now we can go QA result, and I'll just call that system initialize. At the moment, actually making that same mistake again. This is not a C file. Alright, so there's our declaration, and we want to put our definition into our CPP file. Okay, its name and what it's for. Again, the style of comments I use may seem like they're redundant comments, but it's not about that telling me a great deal of detail about what the function's for. It's so that I can spot it quickly when I'm scrolling through code. If I've written some code where I'm not 100% sure I'm going to know, or it's not completely obvious what that code does, then of course it's definitely sensible to be popping comments in there to explain that particular thing. This kind of makes sense though. We're initializing the system. That's what this is all about. Now, to make sure that that's good to go, when we start to add stuff to it, we're going to include boot.hpp here in our main.cpp file. And what we'll actually do is go if system initialize, and because the fail is a 1, or it's a logical true, by doing this it's essentially the same as us going if system initialize equals QA fail. Basically going to do the same thing. We don't need to pop that in there, it's kind of redundant to do that. If you feel that it makes it easier for you to understand when you're going back through, definitely feel free to do it, but in this case we're not going to worry about it. Now, if there is a failure in that system initialization method, we are just going to chuck it straight into an infinite loop, simply because that code kind of needs to occur or to run successfully in order for the system to be at a state where it's ready to go for the rest of the stuff. So our clocks are set up, our caches are set up, all of our sort of power and system management stuff is all done so that the chip is ready to go from there, and then we can start looking at initializing peripherals, setting up drivers and systems and all that sort of stuff on top of that. So that is where we are going to stay for the next few minutes. I do need to take a bit of a brief bio break, so I will be back and we shall start getting the system initialization code popped in there. By the end of the stream, the goal is for us to have the system fully initialized, to get the user LEDs on the front of the device working, much like the particular user LED that we have at the moment. So we can see that we actually have that one. I'm not sure if the stream's just frozen or no, is that just the camera? Okay. Anyway, we can sort of see that we have a green LED that's on below the screen. I'll have to try and figure out what's actually going on with this thing. If that green LED is flashing once per second in the stream, if someone can let me know, that'd be awesome. Because what I'm seeing in OBS is definitely not that, and it looks like it's not actually feeding the video data through properly. Looks like it's happening way slower than it should be, but it might just be because I'm streaming and recording everything at the same time too. So anyway, I will be back in a few minutes. I'm just going to grab a quick break and then we'll get system initialization done. And then we're going to get the GPIOs done so that by the start of the next stream we can actually start to get a bunch of the drivers written and all of that sort of stuff so that we can start to actually get something happening. I'll be back and we'll have a bit more of a chat about what the roadmap is, especially over the next few streams, and what you can expect. So be back in a moment.
Exaggerated, that's what you assume. The story's over now, I must conclude. I am conflicted, watching where I step still, hanging in the balance, not the life I want to live. I want to take it all, standing tall, fear I weighed the person you are. Oh, break out, I've got to see. Spent all my life holding all of it closely. I played it innocent, a feel of discontent. I'm finally facing it all, fearless.
And I'm back. Alright, so, like I said, I'm going to have a bit of a chat about where things are going to be going over the course of the next couple of streams or YouTube videos. By the way, if you're finding it interesting, definitely please follow on Twitch or when this goes up on YouTube. If you're watching this, once that goes up on there, please subscribe if you're interested in this sort of stuff. Like I said, it might seem a little bit boring for the moment, but this stuff's all really important for where we're going to be going beyond this. We are going to be definitely looking at some more interesting stuff, especially once we start getting the actual LCD working and a bunch of the peripherals, things like that as well, touchscreen, audio. As I mentioned before, basically by the end of this stream we want it booting, we want the user LEDs working, we're going to do the typical make an LED flash. I typically like to use the green user LED on this board, and at least one LED on most of the boards that I've messed with as a heartbeat LED, so that I can see at a glance whether or not it's locked up. And in this case, I typically will use the red LED to come on if a particular error has occurred. I'll do things like make it so that if both LEDs are on solid, that would indicate that we've encountered, say, a hard fault or a memory manager fault, things like that as well, or exception. Beyond that, we're going to, in the next stream, be getting some serial up and running. So we're going to be using the USART1 peripheral to be able to have serial communication with the computer, so that we can actually start getting data back. And the reason why I'll typically do the LEDs and the serial first is because they're actually really useful debugging tools. Once we've done that, we are most likely going to go through and start getting the SDRAM driver written so that we can actually get the SDRAM fired up, because we need that to be able to store frame buffers for the LCD screen. Which means that once we've got the SDRAM driver done, and we might also throw in a dynamic memory manager for the SDRAM as well, which is something that is going to be really useful moving forward. Once we've done that, we're going to be looking at getting the LCD screen up and running. Beyond that, looking at getting things like the I2C peripheral set up so that we can communicate with the touchscreen controller. That will also be used down the road to be able to communicate with the WM8994, I think it is, audio codec, so that we can get audio into and out of the board as well. There's a bunch of different drivers that we're going to be looking at. Some of the simple ones are like the real-time clock, the random number generator, things like that. If we have a look at this one, you'll see that I've actually got two of these development boards here. So if I just move the camera down a bit, if that actually chooses to update correctly. Not sure if it's actually showing that yet. But basically we have one of them set up that's got a couple of analog joysticks, a rotary encoder, and a bunch of buttons set up. So we'll be looking at using things like the analog to digital converters for the joysticks, using one of the timer peripherals to be able to do the decoding of the quadrature signal for the encoder in hardware, so that we don't have to use a CPU for that. As well as setting up the GPIOs for the buttons and some of the different things that we can do with those. It doesn't look like it's actually playing very nicely at the moment, at least in OBS. I'm not sure if it's just the preview it's giving me that's a bit messed up, or what's going on. Yep, it doesn't look like that camera's working properly for the stream either, from what I can see of that one over there. So, we're going to cheat a little bit for getting the clock set up and things like that. Firstly, because while we could dive into the actual HAL files and things like that and figure out how to set it up, I've got about 50 different projects that already have clock set up and things like that done. So we are going to be copying and pasting a bunch of that boot code into here. I will, however, go through each bit of it and kind of explain what it does, why we're doing it that way, why we're using particular settings, and things like that as well. So let's just make sure I've actually got the right thing selected there. So if we get another copy of the IDE up and running, there we go. We are going to open up this one, which is just a bit of the test code that I've been working on. to figure out kind of what approach I wanted to be taking with the streams and YouTube videos for these particular devices. Rather than just kind of running in blind. And as we can see, we've got a decent bit of code that's been written for that one. This is all stuff that we're going to be writing and going through, and I'll be explaining, you know, why we're using those particular things. So some of the things that we've already got running in this particular bit of code is a full dynamic console manager, so that we can set up kind of like a bash or DOS style terminal, but in such a way so that we can have multiple of them, so that we can access it using a terminal style interface from a variety of different ways, whether we're hooking it up using the ST-Link serial to the laptop directly, if we want to be able to Bluetooth to it and access it that way, which we're actually going to be integrating in an ESP32 for that sort of stuff, including being able to use that sort of thing to do it over the network, so over Wi-Fi. Other cool things that you can potentially do in that sort of situation is actually go through and open up a file from, say, the SD card and feed that into one of the terminals as a script, so that it effectively goes through and runs that. Hopefully I'm not rambling too much, I just get a bit excited about all this stuff. We have a dynamic interrupt manager, which I mentioned earlier, so that we can actually chop and change interrupts on the fly, which I find really useful. And although it's something that I've done using C previously, the way I've done it using classes in C++ is really kind of cool. We have a memory management unit for the SD RAM, and a serial manager so that we can have multiple serial devices. And again, a bunch of benefits to doing that sort of stuff that way. But before we get sidetracked too much more, let's jump into our boot.cpp file for this one. We're going to take all of this and we're going to paste it into here. And we are also going to put a return statement in, and if we get to this point we know that everything's working, so we're just going to pop in this case, QA OK. This previous project has a slightly different name to it, so I'm just going to go, rather than doing a find and replace, I'll just do this manually because there's not that many of these guys. And then we'll have a look at what this is actually doing. Now, I am a fan of 2 space tabs. And it looks like I haven't actually bothered to set up that for this project. 4 space tabs or 4 space indents can be really useful, but I find, especially on a small screen, if I want to be able to pull up 2 different files side by side, things like that, if I have a bunch of indents, all of a sudden I'm having to scroll a whole bunch more than I'd really like to in order to be able to see what's going on. So we are going to go through and make sure we have 2 space indents set up for this one. Let's see if I can actually remember how to do this. Where are we? There's 2 particular places we're going to need to sort this out. This is one of them. We're going to enable project specific settings. We're going to edit this particular formatter. I'm going to change our tab size to 2. I'm going to need to rename this guy, otherwise it's not going to let us save it because it's one of the default ones. And we'll apply that. Go OK, apply and close, and we're also going to go up to window and preferences, and I believe it's in editors, maybe. No, it's not in there. That's why it's kind of fun doing this stuff live, because there's certain things that, I mean, I only have to do this stuff once for each project, so I don't always remember exactly where it's going to be. I know it's in here somewhere. No, I was sure it was in general. It's not there. Text editors. There we go. Display tab width to 2 spaces. Beautiful. Alright, so that's that sorted. Again, if you like 4 space tabs, use them. Whatever kind of suits you. Programming to me is a lot like handwriting. Everyone has a slightly different style. And as long as what you're doing is actually working for you, just making sure that the stream is still behaving itself. Awesome. It looks like it is. Guess we're going to find out. Yeah, so if you download this code from GitHub and you want 4 space tabs, you can literally just go through and change those settings in the 2 different places that I just showed you, and it will actually change all of the code back to 4 space tabs, which is perfectly fine. So, copied in this system initialization code. First 2 things that it's doing here is setting up the instruction and the data caches for the Cortex CPU core, in order to make sure that we're leveraging the best possible performance out of the chip. I'm not going to go into cache too much at the moment and explain kind of what it does and how it works and all that sort of stuff, because it's a bit more in depth than I'll actually want to do for this particular stream. I do have these 2 guys commented out for the moment, however we are going to come back and uncomment them. In fact, we might just do that now. So the ART accelerator allows the CPU to more quickly access the data that's sitting in the flash memory of the chip, which is where all of our code is going to be residing. So by turning that guy on, it's going to allow the CPU, or more correctly the caches and that system, to access that data from flash quicker, both our code as well as data. Turning on the flash prefetch buffer, again making sure that we're trying to get instructions flowing as quickly as possible through the CPU. We're setting up our Nvic priority grouping, so the Nvic is responsible for handling all of the interrupt and the different interrupts for the different peripherals, if I say it correctly. And there's different ways that you can actually set up the priorities. Some of them will allow you to set like a major and a minor priority value. I like to go with priority group 4 because it basically allows us to give it each of our interrupts a priority between 0 and 15, where 15 is the lowest priority, 0 is the highest priority. That way we're only dealing with 1 priority number, keeps things a little simpler. We're going with HAL init tick and setting the priority for that one. So this priority here is related to what we're doing in the systic handler here. Essentially, as I mentioned before, that's for the system timer, to make sure that is working correctly and at the right priority, because that's something that we want at quite a high priority, because we want that timer to continue working even if the CPU gets stuck in an interrupt or is stuck doing something. It's the best way to explain that. So essentially we want that to continue regardless, I guess. This is the simple approach. Alright, so we've initialized the system tick, configuring the low speed external drive capability. So this is for the low speed external crystal. This is the one that gets used for the real-time clock. So basically just getting all of this set up so that when we do go to actually get the real-time clock set up, it's going to be good to go. Now, in order to be able to set the LSE drive config, we need to enable backup access to that, as it's kind of, there's a little bit of memory and a bunch of registers which are in the backup domain of the chip, which is kind of a separate section that continues running even if the processor, like if we hit the reset button on the front, or if we upload code to it or whatever, that's going to continue running in the background along with the real-time clock. If we were doing something where we were going to set up battery backup so that the real-time clock continues even if the main power was cut, then the backup domain will continue holding onto its data and its registers and things like that, even in that event. Which is why we need to enable access to that prior to modifying it. It's kind of a separate area, if that makes sense. Setting up our main internal voltage regulator, so enabling the power management clock, and then setting up our voltage scaling there. Not going to go too much into all of that stuff at the moment. And then we're going to do our first sort of section of clock setup. So we've kind of got three sort of sections that we go through when we're setting up our clocks. First one is actually turning on our particular oscillators, setting those up the way we need to, setting up our main PLL so that the frequency coming out of that is what we need. The second section we're going to be doing will be making sure that all of our bus clock and bus clock dividers are set up correctly. Thirdly, we're going to roughly set up some of our peripheral clocks as well. Most of the individual peripheral clock stuff I'll do in the particular driver for that peripheral. However, we will actually go through and set some of that stuff up in here as well. So we can see basically filling out this oscillator initialization type def, which we can see in there. Telling it that we want to be using the high-speed external oscillator and the low-speed external oscillator. The high-speed one will be where we get the clocks for most of the system, and the low-speed one, as I mentioned before, for the real-time clock. Turning the high-speed and low-speed external oscillators on, turning the main PLL on, which is the thing that's going to take our 25 megahertz from the HSE and bump it up to 216 megahertz. So that we can drive the system with that. Telling it that the PLL source, or the clock source for the main PLL, is going to be the high-speed external crystal, and then we're giving it the particular values that are going to get us a 216 megahertz clock for us to use. Now, most of this is fairly similar for most of the STM32 line. You will find different devices have different particular frequencies they want to operate at, and you're going to need to be able to figure out what the PLL values are going to be for that, and that's where doing that using the project wizard at the start where we're looking at the clocks, that's where that can be really useful. So we're going to set up those, return a fail value if it fails, because if we can't even set up that, we don't want to be doing anything else. We're going to be enabling our system configuration clock so that we can actually go in and use or start to configure the system a bit more. We're going to enable overdrive for our power system. Part of the reason for that is because we are going straight to the maximum clock speed for this chip. By enabling overdrive, kind of make sure that it's going to run smoothly. This is where we are getting our CPU and bus clock set up. So we're telling it what clocks we actually want it to modify, or what clocks we want to modify while we're doing this. telling it that our system clock source is going to be our main PLL, and then setting up the particular dividers to get the correct frequencies for the various buses. And again, if that fails, we're returning a fail. We are going to go into that infinite loop over here in main, because again, if we can't get that set up, we don't really want to be doing too much else. Now again, there's other approaches we could take here. That's the way we're going to do it for the moment though. I feel like I'm saying a lot. Bad habit. And then we're getting some of our peripheral clocks set up. In this case, the real-time clock, the LTDC, and also setting up the clock source for our USART1 serial peripheral. We are setting up our Psi PLL, which is the PLL that is generally going to be used for the audio input and the output to generate the particular clocks that we need for that. However, in this case, it's also being used for the LTDC peripheral. So if we don't set that up properly, then we're not going to get anything working properly with the LCD screen. Telling it that we're going to be using the low-speed external clock for the real-time clock, and telling it that we're going to be using pclock2 for the USART1 peripheral, which is basically the clock of the bus that peripheral is connected to. There is other options that we could go with in that situation. And again, if this stuff fails, we could handle this differently, but we're just going to return a fail, go into that infinite loop. At this point, I'm going to turn on all of the clocks for all of the GPIOs. There's not a GPIO that we're not going to be using, especially given how many GPIO pins we need for things like the SD-RAM. May as well get all of those turned on now, rather than having to deal with that later on a per peripheral basis. Doesn't make sense. We're also going to be enabling the clocks for both of our DMAs as well, because again, stuff that we are going to be using, may as well get those turned on now. So that is basically all of our initial boot code. To get the system up to a point where it is actually able to start up and kind of ready to go at the clock speeds and everything that we are looking for. Now, moment of truth, let's try building this guy and let's see how many errors we get. Yeah, we don't want code generation for that. Okay, 17 errors. What do we got here? I'm guessing I've left a bit of a comment laying around here somewhere. It's kind of the good thing about doing this live as well, is actually you get to see where I mess up and how we go about trying to find the problem and fix it. Right, I'm wondering if that's doing that because we've got something... No, that's the only place where we're actually seeing errors. I was kind of expecting there may have been a comment that was opened but not closed. Something along those lines. It might even be something that's not necessarily in this file specifically. The other thing we're going to do, while I think of it, just to get down the road, is we've already enabled the power and system config clocks in our boot file. This MSP file can disappear. Get rid of that one. Where does this start? Aha! Alright, I missed a step. So basically, when we set up this project from scratch, If we go into the drivers folder that it's created, and we go into our HAL driver, you can see it's chucked a few files in there. But there's going to be a bunch of them that are missing. So for example, the ADC, we've got no HAL drivers sitting in here for the ADC, which is why we're getting an error there and why we're getting 17 others. One of the approaches I like to take is basically just look at dumping all of the HAL drivers into these folders so that if we want to use a particular peripheral that we haven't enabled yet, we don't have to go back and look for it. It doesn't necessarily affect the project too much through doing that. It just means that there's going to be less head scratching like we're having right now. If we go to... let's bring up this one. We're going to jump into... this one? No. It's this one. Alright, so in your users folder, we should have a folder called STM32 Cube. This is where the repository will be, which is where you'll find all of the different firmwares that it's downloaded. So in this case, I've got the F4 and F7 firmwares. Typically would also have the H7 firmwares here as well, but haven't done much with that since I did the last Windows reinstall on this laptop. I'm going to go into drivers, the HAL driver, the ink folder. We're actually going to grab all of this except for our conf template, our assert template. Not sure if there's any other template files in here. No, just those ones. We are going to drag all of these into our ink there, tell it to copy the files, just overwrite a lot of them. Doesn't matter, they're going to be identical files anyway, so it doesn't really matter if we overwrite them or not in that situation. And we're going to do the same for source. So again, I'm just going to grab hold of all of these. There's going to be a few template ones in here, like the MSP template. And these guys we don't want. Again, not aspects of the HAL that I actually bother using. And we're going to dump those guys in there. And may as well override all of those. Cool. What's going on here? Let's just get it to do not that. I'm gonna get it to do a clean on that one. Build the entire thing. That's gonna become frustrating. Okay, we'll leave that for the moment. I'm gonna figure out why it's doing that, because we definitely don't want it generating code at this point. Let's just do that, and let's see how we go this time around. Time goes so fast when writing code. It's hilarious. An hour and 45 minutes in. And hopefully the stream is behaving itself. Again, I guess we're going to find out. If it's not behaving, I guess we're doing it again at some point. Alright, and built 0 error, 0 warnings. That's what I love to see. And close our configuration file, close our setup file. Alright, now we could pop that code onto the Discovery board and see if it runs, but it's not going to actually do anything at this point. So in order to test that that code is actually working, what we're going to do is go through and set up the user LEDs, make sure that those are actually working. We're just going to roughly set those up in main at the moment, although we will be looking at creating some specific GPIO C++ classes which are going to make dealing with the GPIOs, so things like LEDs, push buttons, that sort of stuff, much easier. So let's go initialize user LEDs. Now to do that, we're going to need a GPIO init type def, and we're going to call him GPIO init and fill it with zeros. Now I'm also going to come in here to this set of code, jump into our setup.hpp, rather than having to look up which pins and stuff we're actually using for the two user LEDs. I've already got them here. Here's one I prepared earlier, as they say. We're going to chuck those into our setup here. Yep, don't want those indented. There we go. And change this. So now the reason why these have got QAD in front of them is because QuartzArk is the project and we're dealing with something that's at the driver level. So the D gets put there. Typically, if I was dealing with something that was related to one of the systems, it'd be QAS. If it was something that was related to the core, so the code, all of the files that we've just created, then I'd probably put QAC. Again, I like to be able to see stuff at a glance to let me know what's going on. So we've got two user LEDs on this board, one of the red one and a green one. The red one, as we can see, is on GPIO-J pin 13. The other one's also on GPIO-J, and that one is pin 5. So that way we can actually just refer to these defines from here, make life a little bit easier for ourselves, like so. Now, particular bits that we're going to need here is the pin, which in this case, let's do the red one first. I'm going to go QAD help if I could type properly. Red GPIO port. We're going to want pin mode. This one is going to be, I believe it's GPIO mode output push pull. There's a couple of different output modes that you can use for these guys. We're going to use the push-pull mode for the LEDs. It just makes the most sense. Again, not going to go too much into why that is at the moment, but when we start to look at various different peripherals, it can make a bit of a difference as to how things work, whether we use an open drain mode, which is the other mode, or the push-pull mode, which we're using here. Now, we have pull up and pull down resistors, but we're not using either of those for this one, so we're going to go no pull and set the speed for that pin. Now, because we're just driving LEDs, we're just going to go the lowest speed possible, and then we will initialize this one. Now, we could check to see whether HAL GPIO init returns an error or not, because it does return a thing to let us know whether it failed or whether it succeeded. Generally with setting up the GPIOs, I don't know if I've ever managed to get it to fail, other than when I've put dumb settings in there. So we're not going to stress about that too much. The first thing that this particular function is going to want will be what GPIO this pin is actually on. So we're going to go QAD user LED red port, which means this should be pin. Always double check your stuff, otherwise it doesn't work. And we're going to pass it that GPIO init structure. We're also going to go GPIO init pin to modify this a bit and go QAD user LED green. GPIO pin. Make sure I spell all of that correctly. That's all we need to modify for that one, so we can initialize that as well. So QAD user LED green port and GPIO init. Let's see how well my memory is actually working as far as getting all of that working correctly. Let's just build that, make sure I got all that right. Where's LED red? Okay. There we go. Need to pop the GPIO in there. Okay, that should build. Yep, fine. Wish there was just a nice way to be able to tell that thing we don't want it generating code. It's actually the first time I've ever had it do that to me, and partly because the file wasn't saved properly when we generated the initial code. And whenever that file gets saved, it wants to generate code. It's just got a bit of a thing for that. Now, what we might do just to finish off for this stream is we're just going to get an LED flashing. We'll look at getting, like I said, some actual drivers done for the GPIOs during the next stream. We might look at getting a few different drivers done for the next stream, and possibly, so like the real-time clock. Maybe. Actually, we might do serial next. So getting a UART driver and serial up and running, because that way once we get the random number generator and the real-time clock up and running, we can actually send data from those peripherals via serial back to the computer, make sure that those peripherals are actually working properly. Alright, so I'm going to go HAL GPIO right, I believe. I'm pretty sure that's what it is. We don't want that one. Let's go. This will get us to the file we want. Let's chuck you over there. And if we go down, typically near the second half of the files, we'll see the various functions that are in the HAL. So all of the HAL files have a relatively consistent layout, which is good. Makes it a little bit easier, even if the HAL stuff can be a bit convoluted and confusing sometimes. In this case though, using it to help us set up the GPIO and turn the pin on and off, stuff like that, I find useful. So in this case, we're going to tell it what GPIO we're using. So in this case, we're just going to make the green LED flash, user LED green, GPIO port, QAD user LED green, no, user LED green, GPIO pin, and GPIO pin set, which will actually turn the pin on and will give us a binary 1 effectively. I'm going to go HAL delay 500, And then we're going to turn it back off. HAL GPIO right, QAD user LED red, GPIO port, QAD user LED red, GPIO pin reset, which will give us a binary 0. Then another 500 millisecond delay, so that it should turn on and off once each second. I'm guessing that should build. No, 2 errors. What have I not typed correctly? Let's just chuck this back over here for the moment. What's the error? HAL GPIO... Oh, yeah, bad memory. It's HAL GPIO write pin. Much as it's got HAL GPIO read pin for reading stuff in. That's better. Alright, 0 error, 0 warnings. That's what I like to see. Let's chuck it onto our device and see what we have. This launch configuration properties is only going to come up once. Once we've accepted all the settings, we can go through and modify stuff after the fact. But for this, it's all good to go. We're just going to hit OK. And then we should see it's going to go through and that message is really annoying. There we go. Alright, downloading it onto the device. I'm not sure how well the camera is working. That is looking at... Oh, might actually be doing it, I don't know if it's failed. And we are getting the LED stuck on. Now notice that there is still stuff sitting on the LCD screen. The reason for that is because that's left over in the actual LCD driver from the previous code that was running on it, which was showing the welcome message. That's perfectly fine. If we were to hit the reset button, it's not actually going to do anything for us. Yeah. So typically part of actually doing the LTDC driver would actually be triggering the reset line that goes to the LCD, which is why it's not actually doing it for us at the moment. So that's perfectly fine. You just got to ignore what's actually on the screen there, because it's not what the code's actually doing. One thing we are seeing though is that our delay is not working properly, and that would indicate that SysTick is not set up properly. I believe that may actually be because I might have missed a step in our handler. Let's double check that. I think there's a second thing that I normally call. I got HAL Intick, which we did pop in there. Now, let's have a look in... What have we set up as the default handler? We haven't set one for that, right? Okay, so that's irrelevant, which means that our error has to be somewhere else. So, let's go to our boot file. I believe we've got SysTick's being initialized there correctly. Right, why is it not working? Maybe indicate potentially that we're not actually getting the handler being called. It's the most likely thing because we're setting up the system tick. We are calling the correct method from the handler. I would expect in that instance that the handler itself is not getting called. This is where debugger comes in handy. So what we're actually going to do is we are going to go into our handlers file. We are going to create a breakpoint right here, and we're going to see if it actually comes into that breakpoint, if we stop on that breakpoint, or if it just continues. So we'll see if that is actually behaving itself, which I'm guessing is going to be a no. Again, warts and all, you get to see all of the stuff that happens. Things don't typically always go perfectly first time, and that's being okay with that kind of makes programming much more fun. I generally don't have any issue if code doesn't want to compile or run correctly first time. That's part of the fun of solving the puzzle. Alright, so we've entered the debugger, which has currently copied the code to the chip, started it up, and frozen us right at the start of our code execution here. So it stopped just prior to actually going through and initializing the system. We're just going to come up here and hit resume, and we are actually calling this guy, which is why it's jumped in here and frozen. Which means Hal Inc tick is actually being called. What's it doing after that? So jump out of that. Let's continue on. Okay, and jump out of that. And that. And that. Doesn't actually seem to be traveling back to our main code. Okay, let's terminate this and get rid of that one. Curious to see what it's actually doing in main. So we know it's getting to this point because we know it's actually turning on the green LED. Again, I'm not sure if what you're seeing is the correct output from that camera. Let's see if I can fix that quickly. Doesn't seem like it actually wants to reconnect. I think that camera is actually not behaving at the moment. Basically got my iPhone set up as a webcam so that it can keep an eye on that one. First time I've used it over this sort of time frame though, so let's go without that at the moment, and let's see if we can find out why we are having this particular issue. Let's just debug that. Technology's great when it works. Let's go with that one. Okay, again, we're just going to resume code execution. We get to there, that's all fine. Sets the states. Then we go into our delay. It's actually getting stuck in there. Curious. You can see from the call stack, we're going to HAL delay and then to get tick. And yet we did see before it was actually calling the handler. Joy. Fun bug. It's got to be something simple that I've missed. Which is hilarious, because it's writing this particular bit of code, something I've done so many times, and yet it doesn't want to work. That one I want boot. And we copied and pasted all of that code from there, so that can't be what is causing our issue. There's nothing I missed from in here. Nope. Again, we'll go through what all of this sort of code does over the coming streams and videos. Pretty much. Finally, you're telling me that that camera's actually just randomly decided it wants to work now? Apparently not. Okay. It's fine. Okay. It's definitely a bit of a weird one. Don't know if it's... Oh, there we go. One of the other tricks that I find may not help solve it in this particular situation, but it's something that I like to use as a bit of an approach, is if you're trying to find a bug and you're looking through the code and all the code you're looking at is correct and you've gone over it numerous times, the bug's probably not where you're looking. So we will just double check that this all looks correct here. We are definitely doing init tick. Indent's not right either. Fix that up while I spot it. Alright. It definitely looks alright there too. And as we saw before, it's definitely calling that guy. Hope this is entertaining. You used to be the sort of person that would just get insanely frustrated by bugs, and learning to just be a bit chill with them makes life so much easier. It's fine, they're gonna happen. Just half the challenge and half the fun is actually finding them. Okay. So essentially what InkTick is doing is actually just incrementing this by the tick frequency, which in this case says 1 kilohertz. So that all appears to be set up properly. However, this guy's not incrementing. It's not on 0, but this is the first time through, so let's keep going. Let's just tell it to go until it hits that breakpoint again, so we'll resume it. Jump back in here. Step past that. It's now got a 2 in it. So that's actually incrementing. And one more time. Cool. Step past that line and it's gone from 2 to 3. So ink tick is actually doing what it's supposed to do. And then if let's just terminate that debug session for the moment. We'll jump back into main.cpp. If we go into HAL delay, we can see it's basically getting what the tick is at that particular point, delaying until get tick minus tick start is less than wait. Okay. Which is strange because that kind of says that it should actually be working. This is a bit of a weird one. I like a good challenge. What we might do though, because this stream has gone on for a couple of hours now, is we might not worry too much about that right now. We're going to do a bit of a hacky approach to this just to actually see that our LED does actually flash, and that the issue is related directly to HAL delay. As long as that works fine, we might end the stream there. And I'll have a bit of a look into why our SysTick is not working correctly, which is strange. I've never had this particular issue before, and I guarantee it's something simple. It always is. And I always love the bugs where it appears that it is actually functioning correctly. We can see that the handler is increasing the tick value. We can see that HAL delay is doing what it's supposed to, but for some reason the HAL delay is not seeing the tick value count the amount of times to give us 500 milliseconds, and is getting stuck in that loop. That was a mouthful. Alright, so let's just call this timer, and let's go timer equals 0 while timer is less than let's go, this might be a bit slow, we don't know yet, find out. Timer is less than 10,000, could be a bit quick, we don't know yet, but so basically create a timer value, increment it 10,000 times, and then it'll continue. So basically doing our own kind of delay there, and see how that works. Yeah, go away. Okay, build's okay, let's chuck it on there. Okay. Wow. It's actually doing exactly the same thing. Oh my god, you guys are probably screaming at the screen right now. Pretty sure I would be. Because I've just spotted the silliest thing possible. Let's comment this out. I don't think the issue was with HAL delay at all. Like I said, typically if you can't find the error, it's not in the place you're looking. And it was right in front of me the whole time, I believe. So we're turning the green LED on, but it was a red one that we were turning off. That's a bit silly right there. Let's see if that actually gives us what we want. Yeah, getting a warning for the unused variable, that's perfectly okay. Yeah, come on, pop it on the net. Let's get it happening. And we have flashing once a second. I don't believe that camera is actually working properly. And if you guys are seeing what I'm seeing in the OBS preview, it looks like it's actually stuck on. However, if we jump to this view here, we can see we are actually getting flashing of the green LED once per second. So, working correctly. However, that was a fun adventure, all because someone doesn't know which color they're supposed to be writing in the code. So now that we've sorted that out, let's do a bit of that, like that, because we know that actually works, just like it's supposed to. All of our files are saved. Now, I would recommend using GitHub. As you saw, we created the repository right at the start for this project. One of the weirdnesses is that it's worth making sure that you close this IDE prior to doing a push to GitHub or to doing an incremental backup to your hard drive or whatever. Simply because if you take a project from prior to when the IDE shut down and you try to load it back in, it can sometimes be a bit weird because there's certain things the IDE does to the project when it closes, which is again one of those quirks of the CubeIDE. If anyone from ST watches this, love your products, like genuinely, definitely not being sponsored by them, or I would love to be. However, there's certain things with the software that could be better, but if I had to select a particular microcontroller family to be working with, it would be the STM32 family all the way. Second favourite would probably be the ESP32 from Espressif. Okay, so saying that, we'll close that one. And we shall end the stream with a bit of a push of this one. Why is it not seeing changed files? I think we closed the wrong IDE as well. Yes, exit both of those guys. Now, I'm thinking I put the workspace in the wrong folder here somewhere. Let's see what we've got in here. Right, okay, so we've saved it into this folder when this is actually the Git folder. So we're just going to pop that in there, and then we're going to make sure that when we reopen that project in CubeIDE in future, that we're pointing it to the correct directory. Okay, so always try and give yourself a bit of a hand. It's always nice when past you has actually been slightly helpful. Try and keep a bit of a good description when you go to push your project to Git, so that you at least knew what you did. So it's initial boot codes and testing. System initialization code done and working correctly. Not too much else that we're going to add to that. I could put in there that we got GPIOs working, but that's not how we're going to be doing them anyway, because we are going to be writing a special driver class for that. So let's commit that guy. And I'd like to say, for anyone that has stuck around this far through this particular stream, thank you so much for watching. This is something I find a lot of fun, and actually getting to do streams and videos and share all of that sort of stuff with people I think is really, really cool. So I look forward to more of that. Now, obviously, there wasn't very many viewers on this stream, and that's perfectly fine, because hopefully people are going to get to see this at a later date, either on Twitch or YouTube anyway. Just jump back to that one, because you guys were missing what I was actually doing there. So basically popped in the comments, committed it to our main branch, and we're pushing that to GitHub. Now, I believe the particular address for my repositories is github.com ones and zeros. Is it that one? Yeah. Alright, so now, although this one's set up as private, at the moment I will actually make a fork of that is, or make a duplicate repository of that one that is public, so that stays as the particular code base or the code that we worked on from today's video, rather than going and adding to it with the next video, so that if anyone just wants to see just the stuff that we've dealt with in this stream or this video, they'll be able to do that without actually having any issues with that. So that's all been pushed to Git. Again, thank you so much for watching, guys. If you've got any questions or comments, feel free to leave comments. You can also send an email, and I haven't actually set up the email to show in OBS, which I will do for the next stream. However, you can, if you use Reddit, also jump onto r/ones and zeros, as we can see down the I will be looking at questions and stuff on YouTube, on Reddit, as well as the email address, which is ones and zeros, so 1s and 0s .contact@gmail.com. So that's the contact email address. I think there's links to that on Twitch. I believe there's also a link to that email address on YouTube as well. If you're watching this on YouTube, I will pop a link in the description. If you've enjoyed it, please drop me a like, subscribe, hit the notification bell, all of that sort of fun stuff. And I believe there's a personal assistant that actually believed that I was talking to her. Upset to find out that she was not actually who I was talking to. So thank you again. Look forward to the next stream. I'd say I will likely be streaming again tomorrow, and we'll be getting into some of the more fun stuff now that we've got all of the foundations for our project done. So hope you guys have a great night or day or whatever it is, wherever you are, whenever you're watching this, and thanks for watching.